terms of black hole growth. And I'd like to argue that it's just the opposite. That in fact, feedback-free starbursts can give rise to very efficient black hole growth. So, just to remind you what you heard about already a few times about feedback-free starbursts, summarized in those two papers, it's a robust prediction at high density and low metallicity. It's not a fix-up because of the observations. Okay? And the prediction is that you must have, at redshift around 10 and massive halos, high star formation efficiency in this sense. At low redshift, you expect lower star formation efficiency because of feedback, various kind of feedback. So you get high star formation efficiency if you are feedback free, and I argue that this happens under these conditions. Characteristic time scale of million years, densities of 3,000 per cc, and surface density of a similar number of solar masses per parsec squared. So these are the necessary conditions for FFB. One, to be free of supernova and stellar wind, you want the star formation to be faster than the lifetime of the massive stars, which is around 3 million years. To get the free fall time of order million years, you want this kind of gas densities. To be free of radiative feedback, you want gravity to confine the radiative pressure. This requires a surface density of this sort. Combining those two, telling you that you need clouds of about 10 parsec, globular cluster-like clouds. You need cooling down to temperatures of star formation on a free fall time to get a burst such that this window of opportunity will materialize. And this also requires, surprisingly, a very similar constraint, for metallicity of about 1%. You also need shielding against winds and UV from earlier stars, which are now providing feedback. And this requires that the clouds will be more massive than something, 10 to the 4 solar masses. 10 to the 6 solar mass clouds are perfect for this. And finally, or firstly, you need the cold streams to bring in a lot of cold gas into your galaxy. In other words, you don't want the halo to be too massive. If all these are fulfilled, then FFB is guaranteed. And in fact, this is summarizing this constraint. This is the 1 million year feedback window. This is the free fall time as a function of density. And you see that at a density of about log of 3.5, the free fall becomes shorter than the million year critical time. Also, the cooling just happened to cross at the same kind of density. So these constraints all give you this kind of behavior of FFB in this regime. I don't know why it's jumping so much. It turns out that either in case of a spherical shell or in the case of a disk, very naturally, at redshift around 10, you're getting number densities behind the shock of about the critical density that you need for FFB. This is because the Mach number here is about 15, and you have a big jump behind the shock of this kind of density. And here it's because of the angular momentum of the streams typically bringing a gas into the disk. So FFB densities arise very naturally at the right redshift. Now, the story is that you need to accumulate enough gas for the fragmentation to happen, either in a shell or in a disk by disk instability. In this case of a disk, its atomic mass is slightly above 10 to the 6 solar masses, and you need each time the gas to accumulate here for the Q parameter to get less than unity, such that fragmentation to clouds is happening. And to do this, each time you accumulate about 1 billion solar masses in each generation. Same thing here, you need to accumulate enough gas for Jeans stability to materialize into Jeans clouds. So the story is that you have FFB in generations in some outer shell. All generations provide feedback. Fresh streams come in, and this is the FFB cloud. This is where FFB happens. Each FFB takes about 1, 2, 3 million years, and we have about 10 generations across a whole period of galaxy formation of about 100 million years. This jumpy thing. So we predict this kind of behavior, periodic behavior, about 10 generations of 10 million years each, with a peak of about 1 million year and a peak star formation efficiency. Now, observationally, Giorgio showed yesterday, this is a universe machine prediction of standard model. This is the FFB model, this toy model, in 2 cases of maximum efficiency. This is the Madao plot, star formation rate evolution. And you see some data agreeing with maximum efficiency of about 1/3. I interpret this as the duty cycle of the FFB phase. So the model predictions are between the blue and the orange. And the same thing about the luminosity function, different redshift. You can put in the data, and again, similar conclusion. FFB with a duty cycle of about 1/3. We predict this behavior. This is first result from a simulation that we're trying, showing a very similar behavior of the star formation history. So, and we can predict gas fraction, metallicity, dust, and outflows, all based on a steady wind solution of this configuration. I'll describe in this way. So I want to focus on the black hole formation and try to trigger your interest in this possibility. It's just a feasibility test, because it may or may not work. So this, you saw this from Roberto's talk. The very interesting, intriguing result is not only the rapid growth of the black hole, which requires intermediate mass thin black holes, but the very high black hole mass over stellar mass. And that's what you want to understand. How do you get this compared to the standard? Now, here's what you have. You have about several thousand globular cluster-like objects inside a very compact disk. That's the configuration that FFB gives you at redshift 10. First, you want thin black holes. of about 10 to the 4th solar mass to form by core collapse in those young rotating clusters. And you want it to give you this 1% mass of the black hole. That's the key. Second is, these clusters interact, they disrupt. The black holes migrate inwards, suffering dynamical friction from the stellar disk that has formed, and go to the center. They should do it efficiently enough to reach the center and build the black hole as Roberto wanted it at redshift 7, 6, 5, very rapidly. You need to overcome a bottleneck, which is the recoil when the black hole merge. There's a recoil that can be very fast and destroy and remove the black hole from the center. You want to make sure you solve this and the final passing problem. And it turns out wet compaction can help you boost this black hole growth. So I want to quickly go through these 4 stages and see how realistic they can be. So the synth core collapse, that's a very interesting problem. What you need to do is during the first 3 million years, as long as the massive stars are still alive before they die, you want rapid inward migration by segregation, two-body interaction of the stars, and the massive stars help you. And you get this thermal instability by Lindenbell and others, where a hot core causes energy outflow. As a result, the core contracts and the core heats up because of the Wien theorem, negative specification. That's the famous core collapse, and it is being sped up by the mass function, by having a young cluster with many, many massive stars, especially if it's top heavy, IMF. Another mechanism, which I discovered only last year, something that should be in the textbook, and it's called Bravo-gyro instability. Now, who heard about Bravo-gyro instability? Raise your hand. Are you my student? Don't count. You heard it from me, Mark? No? No? You heard it, yes. A guy called Achisu in 79 thought about it, but it's trivial. It is just the same thing, but with angular momentum. If you have a rotating core, you have angular momentum outflow. The core contracts in reaction, and the rotation speeds up because the moment of inertia goes down. Another trivial result, but you can speed up your core collapse by having a rotating and flattened cluster. And that's really a magic combination to get the core collapse in less than 3 million years. And that's the key. It turns out that this would be the expression for the core collapse time for a given radius and mass for the cluster, and the maximum mass of the stars is the most important, and the black hole mass is indeed on the order of 1% of the cluster mass. Indeed, in simulations, this is one that we are doing at redshift 9, you get a very nice disk, stellar Ugazo's disk. They look very much like disk at cosmic noon. Thick, but rotating disk. In rotating disks, when you fragment into clumps, the clumps are rotating, giving rise to Bravo-gyro instability. This is from a paper by Severino et al. This is the rotation support in many, many clumps in the disks. And you see that there are very high numbers here. Most of the clumps that fragment from disks at cosmic noon, probably also at cosmic dawn, are rotating clumps, subject to gravitary instability. So now I can plot this line here in the mass radius diagram for the clusters, and for a given IMF, you need to be below this purple line for the core collapse to happen in the time that you have, the time window that you have for FFB, the 3 million years. That's this line. This is what characterizes the density for FFB clusters. So you must be below the red line and below the purple line, for example, in here. Okay? So a nice solution that can happen in the right time under these conditions of those young rotating clusters is black hole seed of 10 to the 4 solar masses inside typical cluster. This is the mass of the black hole. In a typical cluster of 10 to the 6 solar mass. And of course, if you have a higher top heavy IMF, you get bigger clusters, bigger black holes. Stage 2. You put those clusters, this is just a sort of a disk. Here's the center, that's the radius. Forget about the colors. You start with all those clusters with black holes, and quite quickly, in a few orbital times, the clusters disrupt each other because they move at 100 kilometers per second, and they have internal velocities of only 10 kilometers per second. Very quickly, you build this component of disk that is ready to exert dynamic friction on the black holes. And Druba, who is going to talk later today, actually tested. Okay, here's another. I learned a lot of new physics here. You would be surprised that there's no textbook equation that tells you what is the dynamical friction in a disk. Some of you maybe needed it for some reasons. We need it here. You want the black hole to migrate. I looked for some formula. There's nothing. Some remote planetary people try this, but we have to reinvent this. Neil and I and others. And we kind of invented just taking Chernozega formula and put it in a disk. Now think about a disk. You would think, well, you should think that because it's a disk, rotating disk, dynamic friction would be much stronger than in a sphere. And that's because it's the relative velocity between the perturbed object and the little particles that matter. And it's in a disk, it's only the dispersion velocity, it's not the rotation velocity. It goes like 1 over velocity squared in Chernozega formula. This one here. Okay? So, anyway, you can do it very quickly, and this is what you get. So, this is the black hole growth in time, and we start at redshift 9, say, 2 approximations for a cold disk, a hot disk, for dynamic friction, and this is the target that Roberto put for us. Put in these papers where they look at these black holes at redshift 4 to 7. So quite remarkably, you can do it in time, and you get the ratio of black hole mass to stellar mass in the right ballpark. That is your target. So because it's all happening in a disk, it's so efficient. And the disk comes in, giving you the rotating clumps, which speed up the core collapse, and giving you the very fast dynamic friction, speeds up go to the center. And you get this black hole that you're looking for. Now finally you have to overcome the bottleneck of recoil. This is the GR result given the mass ratio of two black holes colliding, depending on the spins and the alignment of the spins, what's the recoil velocity? And you see it easily 100 kilometers per second. It can be 1,000 for spins that are very misaligned. So you have to overcome this. We put this into simulations. So we do Monte Carlo simulations. This is like 5 different sequences of mergers, which we throw in with some mass function for the black holes. So look at the green one, for example. You go and you recoil, so you go away, you start again, you go away, but eventually you start drawing a black hole. So once you're big enough, then the ratio with the incoming black hole is so big that the recoil is weak, and then you survive. But the blue one never made it. Always was recoiled and you couldn't grow. So this is the bottom line result from this kind of Monte Carlo simulations. It's the escape velocity required to retain the black hole in the middle, not get rid of it, below the escape velocity. So if you have a cold disk where the spins are pretty much aligned with each other, then you can do it with 200 kilometers per second escape, which is the typical FFB galaxy. But if you have a hot disk with a lot of misalignments, you end up needing an escape velocity on the order of a few hundred kilometers per second. And this you can get only if you have compaction events. Compaction event like this one, in which, as a function of time, gas compactifies by a merger, and then the black hole starts drawing inside it, and the escape velocity, the black hole spirals to the middle, as you can see in this paper. And the point is that wet compaction helps you in several ways. It helps you by boosting the escape velocities and preventing the recoil, also preventing core stalling during the earlier phase of migration inwards. It also helps you with drag of gas and the final passing problem. So let me conclude. Feedback-free starbursts are a robust prediction once you are in this kind of density and surface density, and we predict a high star formation efficiency. Predicted, okay? One needs to measure it, but we predict it. It's not an excuse to explain the observation. It's natural that the redshifts we are talking about and the halo masses we are talking about, this is the kind of threshold we predict for FFB. And in case of a disk or shell, we expect globular clusters-like objects to do this. We provide many observable predictions. It has to be above a given redshift, a given mass, a given stellar mass, with a typical star formation rate, compact objects. First star formation history is predicted, and that's great because it also helps boosting the luminosity. A top IMF may help, but not necessarily. Outflows of 1,000 kilometers per second, and little gas, dust, and metals with the cold streams. What I told you today is that there is a physical mechanism to draw the black holes the way we want them. FFB clusters provide natural sites for black hole seeds by rapid co-collapse because the clusters are young and rotating. That distinguishes them from clusters we know and love today. The migration in a compact stellar disk can take only half a gigayear. The recoil can be suppressed if the disks are cold enough, and some of you told us about morphology that there are some cold disks, But if the disk is not cold enough, unit compaction that anyway happens, bringing in the gas, increasing the escape velocity, and retaining the black hole from the recoil by a deeper potential well. Thank you very much.
Thank you. I think we have time only for one question while the next speaker prepares.
Thank you, Avishai. So I have no issue following the qualitative picture, but regarding the core collapse part, do you think the FFB clusters are fundamentally different from globulars today?
Yes.
In what way? Because I see the
sign. In two ways. They have the young stars. Globular clusters don't have massive stars.
Okay.
So there is no segregation.
So segregation is more efficient.
Segregation is very crucial. And the second thing, they're rotating. Globular clusters today are not rotating.
Okay.
Those two things give you a factor of 100 in the core collapse time scale.
Interesting.
That's the magic. Yes, so?
So the only difference is rotating.
No, but today...
I'm not talking about today. Modulars for young...
If they had a history like these FFBs, yes. Maybe those FFB are protoglobular clusters. But, yeah. But frankly, this is a major difference. Today, globular clusters take them ages to core collapse. But these guys core collapse in free fall time. Okay? It's very, very different. You must be young, have these massive stars, and you must be rotating. Otherwise, you won't make it in time. And it won't be a 1% mass. Now, take it with a grain of salt, okay? A lot of the physics I described today is wishful thinking. You know, it's handful because it's not really well. We need to do simulations, probably show this working. So this is just a feasibility idea to be studied.
Thank you very much.